Hello, this is my Physics 2211 Lab 4, where we are modeling spring oscillations. So the scenario we're dealing with was modeling the motion of a mass oscillating attached to a spring. There are two fundamental principles at play here. Newton's second law, the momentum principle, stated here as the net force is equal to the change in momentum divided by the change in time, and the energy principle, where the change in the energy of the system is the work done by the surroundings, and also heat, but we're not working with heat in this lab. And the electronic tools used were the tracker and GoScript with a Python code for modeling. So we have a couple important starting equations, the position update formula, which can be derived, and the velocity update formula, which can both be derived from the momentum principle. And we also have the formulas for kinetic energy, gravitational potential energy, and spring potential energy. And it's important to note that energy is a scalar, not a vector, like velocity and position. So the scenario we're working with was when we're using Newton's second law, the system is the mass that's oscillating only, because then we can apply the velocity and position update formulas as before by looking at the forces acting on the system. Now when using the energy principle, we set the system to be the mass, spring, and the earth, and it implies that there is no work being done by the surroundings because instead we have potential energy. So the sum of the changes of all forces at play must be zero, because there's no work being done by the surroundings, so it's just the change in kinetic, gravitational potential, and spring potential energy on the total system. So the goal of this lab is, by using both Newton's second law and energy principle, it's to effectively model the motion of a mass oscillating on a fixed spring while observing changes in energy and motion as accurately as possible. So let's take a look at the video now, and here's a few notes about it. This is not my video, but the entire class was supposed to use it. So here is the mass oscillating. So I used tracker to track 100 data points, and it was plotted here. This is just in the X position. There's also Y position, which we'll look at for the graph in a moment. And this is the mass oscillating on the spring, and we have certain settings as well. So this is for the code itself, that we have the initial values for the mass of it, the initial position, and the velocity. It's 0. The velocity is 0 because it was dropped from rest. This is where the data gets inputted from the CSV file that we get from the tracker data from itself, and then we start at t equals 0. For the initialization, actually with constants, we have 9.8 meters per second squared for the gravitational constant, and we were given the spring coefficient, which is k, 6.83 newtons per meter, and also the unstretched length in static equilibrium, 0.123 meters. And there was given values, and this is to update the spring itself, so we get the vector, the direction, and the s, which is the distance stretched minus the unstretched length, and also energy calculations, which we stated before. And this is the predicting motion loop itself, so we have the initial energy values, gravitational and spring forces, the velocity, position, update formulas, which we stated before, updating the energy values, and now we can look at the model itself. So when we run the program and choose the data file, we see that the motion itself is pretty close. The red is from the data itself, and then the blue is the model. And we will look at these energy graphs, the position graphs, and the x and y position in just a moment. So here's the X position oscillation comparison graph. So the blue is the model itself, and then the red is the experiment. So it's pretty close overall. You can see the amplitudes are about the same, and the measurements themselves are very close. Now for the Y position oscillation, the amplitudes are a bit different, but we'll discuss that in a bit, and also the data points are just about the same overall between the model and the experiment. And so this is the energy oscillation comparison graph. So we have delta K fluctuating, and we have delta U gravity and delta U spring. Remember, these are the change in energies, but we have those two, the gravitational and spring changes in potential energy, opposite of each other. And because all of these cancel out, we see that the total change in energy, delta E, is 0, just as expected. So the energy principle is conserved and correct here. So the period calculation and comparison, we can do that by looking at the two graphs for the period of the X position oscillation and the Y position oscillation. So we can find the periods to be 1.644 from the seconds for the X position and 1.520 seconds for the Y position. So these are different because the masses change differently in each direction, because it changes more in the X direction and the Y direction overall, and there are also different things working on it. So the gravity is for one, and then the spring is for the other more, and so that will change the data itself. So a couple sources of error and assumptions. Few assumptions were I had to have appropriate calculations for energy, make sure I had to assume that the given values in the video were correct. Mass of the spring was negligible because we only were concerned about the oscillating mass at the end of the spring, and that the initial speed was actually 0. A few possible sources of error were position variance when I was actually trying to get the position data in tracker. I had to do that by eye, and then rotation of axes, I actually rotated a bit, 0.5 degrees from the horizontal, negative 0.5 degrees from the horizontal. Thank you for watching.